Navid?
No?
Yep, I can hear you now. Can you hear me? Hello? Could you enable your microphone?
Hello, John.
Yeah, can you hear
Can
me?
you hear me?
I can hear you, yes.
Hello? John?
Can you hear me now?
Yeah, I can hear you now, yeah. Thank you.
Okay, good. So, is your exam tomorrow?
Exams tomorrow, yeah.
Okay, what should we do today?
Can you if I got the thing up, great. Can you explain more of general relativity for me? I don't exactly fully understand it.
General relativity.
General relativity, yeah.
Okay. Are you all right with the special relativity?
Well, not much. I mean, qualitatively speaking, no, I'm not.
Okay,
The qualitative effect.
right. So this part that's all special relativity, and then from which section is it called? Is it general relativity?
Let me see.
So this whole thing. Yeah, so
It's all special relativity. It's just focused on special relativity and it doesn't matter, right? It's focused on the worksheet then.
yeah, it's like this whole sheet looks like it's for special relativity.
Okay, that's fine. Yeah, sure.
Yeah. I think for your tomorrow's test, you definitely so they'll be testing a lot of things, right?
Yeah.
Including like nuclear energy,
Yes.
binding energy, and things like that.
Yeah.
Yeah. First of all, I think you need to know how to do the Lorentz transformation.
Okay.
So this is what we looked at in our last
Previous
lesson.
tube. Yeah.
Lorentz transformation. So Lorentz transformation deals with events. So when and where things occur.
Okay.
That was given by x dashes was gamma, things like this, x minus v t. So I showed you the equation before.
Yeah.
And also there is equation for velocity addition problem.
We have learned that. We learned velocity addition, yeah.
Velocity addition. So that's like, yeah, there's another formula for that one. And then there is relativistic kinematics. So the kinetic energy is given by, so there's an equation E squared is equal to
P squared C squared plus M naught squared plus
P squared C squared plus M naught squared
C squared, yeah.
Yeah, so this one here. So this one gives you the relationship between total energy. And this one is the rest mass energy. And this one is momentum, isn't it?
Yes.
Momentum. You quite familiar with this equation?
I'm familiar with this equation, yes.
Okay. So, and also there is another formula, which I forgot. That is was one here. So this is another textbook. this chapter here. Scroll down. This length contraction. That's just baby stuff. There is the kinetic energy is given by gamma minus 1 m naught c squared.
Okay. All right. And is the wait a minute? Have you enabled click on the screen?
Sorry.
Can you enable the click on the screen thing so I can see where my cursor's at?
I cannot see your cursor now.
Can you enable it?
Yeah. You can. I can give you the control. Yeah. You can use your mouse.
Oh, yeah, fine, sure. What is this called? I know this is rest mass energy. What is this called?
M naught.
M naught. No, gamma M naught.
Gamma M naught.
Gamma M naught C squared. There's a special name for the energy, isn't it?
I'm not sure if there's a special name for it. There's a rest mass energy, which is m c squared.
That's this, right?
Yeah.
Okay, fine. There's no special name for that. Okay.
I don't think so.
Sure. Okay.
So the kinetic energy is given by gamma. So gamma is usually greater than 1, isn't it?
Yes.
So if gamma is 1, that means it's not moving.
No.
Then if it's not moving, it's 1 minus 1, then kinetic energy is 0.
Yeah.
So it's whatever. So if gamma is like 1.5, then the kinetic energy is 0.5 times by the mc squared.
Yes.
Yeah. So it's whatever the leftover bit. That's the kinetic energy. So I would say this energy, this equation is really important for your test tomorrow as well.
Yes.
That's the kinetic energy equation here. So it's definitely worth trying these questions if you. I'm not sure if you're familiar with this question here. Yeah, this one gives you very good understanding into kinetic energy stuff. So
sure.
The question here is calculate the speed of an electron that is accelerated through 1 megavolt. Then it's going to have a 1 mega electron volt. That's how much the kinetic energy it'll have.
Yeah.
But then because electron has gone through 1 mega volt, so the energy it gains is
1 electron
volt. So and then you use this equation. So that's 1 mega electron volt. So what this equation let you find, it lets you this one forces. So if you actually use 1 mega electron volt and let that equate to mv squared, sometimes you find this one greater than the speed of light. So we're no longer using this equation now. So we use this one now, and this helps this it suppresses the velocity so that the velocity is always less than 1c.
1c.
Yeah. So you plug in 1 mega electron volt there. The rest mass energy of electron is always this guy here. So we get 1 mega electron volt is equal to gamma minus 1, and then the m naught c squared, but this bit is 0.5 mega electron volt. So you get the 2 equals to gamma minus 1. So you get gamma equals to 3.
Yeah.
From the fact that this is equal to 1 minus v squared on c squared, you can figure out that the v is equal to 0.94c. That's that one there. And this one is, you got, this question is, just quickly, calculate the potential difference required to accelerate the velocity to 0.8c. So it's just the other way around. 0.8c will give you gamma this much. So plug that into the kinetic energy. Then you get this much energy. So it must be accelerated through this much voltage. That's the question there. So that's no problem. And then there is this these equations. This one is using Pythagoras theorem. But this one being e squared, this is a p c whole squared. And this one is the m naught c squared. It's actually e. There's no square here, but the Pythagoras relationship forces them to be squared, right?
Yes.
Yeah. So think about a triangle. This guy's there. And, yeah. So it says, what is the momentum of an electron with this much kinetic energy? So the total energy is rest energy plus kinetic energy. Kinetic energy is 1 mega electron volt. So total energy is 1.5. So this is 1.5 mega electron volts. And this one is 0.5. So 1.5 square is 0.5 square. So the momentum must be 1.4. And just be careful with the unit for momentum. Energy is in mega electron volt, and the kinetic, the mc square will also be the mega electron volt as well.
Yeah.
But momentum is a mega electron volt per c.
Per c. Okay.
Yeah. As long as you put this number, then you can use the same unit. You don't have to convert it to joules.
Okay. All right.
And the first we can find, so this one here is question 2. What is the speed of an electron with a momentum of that much? So we plug that into
the equation.
The equation. E squared is equal to pc squared plus m naught c squared squared. Well, plug it in here. Then, so c cancels out, right? This is per c. This is c there. So this is 2 mega electron volt squared. And then this is an electron with momentum of this much. We can figure out the total energy. Total energy. This one is 0.5 mega electron volt squared. So we can figure this is a 4 plus 0.25. That's a 4.25. So take square root. That's E, isn't it? That's what is the speed
of an electron?
So we get 2.06. This will be, I think, 2.06 mega electron volt, and then you take away the rest mass energy. So you get minus. So kinetic energy is total energy minus the rest mass energy. So this will be 1.56. Hold on. So there are 2 ways of doing it. One way is this one here. Hold on. So that's total energy.
Yeah.
It's 2.06. They're using this method here. Yeah, you know, kinetic energy was a gamma minus 1 mc squared, wasn't it?
M naught c squared, yeah.
Yeah, if you add kinetic energy with m naught c squared, then this will be gamma m naught c squared, which is the total energy, right?
Total energy.
Yeah. So we already found out the total energy. So we don't have to use this equation to figure out the. So we can actually use this one here. So this is a 1.56, the same thing. The gamma minus 1, and then m naught c squared. So this one here was 0.5.
Yep.
So it's a 3.12. It's gamma minus 1. So it's a gamma is equal to 4.12. Same thing.
Same thing. Okay.
And then the v is equal to, through this one is equal 1 on through it. So v is equal to 0.97.
Yeah.
All good?
Yeah.
So this stuff is special relativity. Now, as for general relativity, it's just I think if you look at your unit outline, it only says qualitative.
Yes.
Stuff, isn't it? So it shouldn't be involving much mathematics.
No.
In general relativity. So this is general relativity, and there is, first of all, the principle of equivalence. So it means no observer can determine by experiment whether they are in an accelerating frame of reference, like here,
Yeah.
or in a gravitational field. So if you are in an enclosed, so that's why these two are equivalent. So and for example, if you're in a spaceship that is accelerating nothing at 0 meters per second,
Yep.
that's equivalent to free fall.
Okay.
So it's very, very confusing. So there's principle of equivalence. I think that's what you need to know. So time slows down. You need to know the time slows down inside. Inside. For example, if you are moving forward at a certain speed, and if you are accelerating, then
Yeah.
time slows down inside the spaceship, right?
Okay. Yeah.
So in special relativity, we learned that when something is moving, then time slows down. True.
Yeah.
But we also learned that through twin paradox, each person observes that the moving frame's time is slowed down.
Yes.
But when acceleration is involved, then definitely objectively the one that is accelerating, the time for that slows down.
Okay.
So therefore, any frame that is accelerating, time slows down. In the same way, if you're under gravity, so Einstein used this equivalence principle to figure out or predict that just as moving accelerating frames time slows down,
Yep.
gravitational something that's under gravity time also slows down.
Okay.
Yeah. So this is another situation. Light has to also bend. Let's have a look. This girl is moving upward, but then within the frame of the elevator,
Yeah.
it appears as if the light is bending.
Wait a minute. You're saying, like, in the perspective of the elevator, or in the perspective from the outside?
Now, from outsider's perspective, the light definitely just travels forward, straight line.
Okay.
But within the elevator's frame, it appears she will feel like the light is bending.
Okay.
So if you are on Earth, in the same way, if you are on Earth, then light has to bend.
Light has to bend.
The light definitely bends.
Okay.
Because we are. So if you are inside gravity, then that's as if you are in an elevator, which is moving upward. But it's actually just a different perspective. If you're in a non-gravitational frame, then you observe this light to not bend. It's just actually traveling straight line.
Okay.
This is a bending of light by gravity. So for the light to exit each box at the same place in a G field, the light must have followed the curved path. That's what it's saying there. And instead of light bending, maybe it's the space and time that it moves through which is bent.
Okay.
This is just another perspective. In reality, we have found that if there's a star and during solar eclipse everything gets blocked.
Yeah.
And we get lots of stars around the sun. And what it appears that the star is actually here. The actual position of the star is actually it shouldn't really be visible. See the star over here? A little out here, I think that could be a star.
Yeah.
Or this one here. This is a star, and that's another star here. So this guy named Arthur Eddington, he almost risked his life to take pictures of this in some African place, and he took photos of this and then identified what sort of stars these are, and then he confirmed that Einstein's general relativity on 1990. So one of the features of gravity is, general relativity pretty much describes what gravity is. Gravity is not a force. Gravity is bending of space-time. So in reality, it's not really the light that is bending, it's actually the space-time that is curved. And light is actually just traveling a straight line through what is a bent space.
Bent space.
It's a bent space, but from the perspective of light, he's just traveling in a straight line.
Okay.
Yeah. Pretty difficult stuff. All you need to know from this one is the equivalence principle, right? And then the fact that gravity and accelerating frame are equivalent, and therefore light in an accelerated frame, if you're looking from outside, light is just traveling straight line.
Yeah.
But if there's gravity, then it distorts the space-time. Light is traveling straight, and because the space is distorted, light appears to go in a curved path.
Okay.
Yeah. Another way to think about it is gravity, general relativity, space-time. Sure. So if I can show you. Yeah, I think. Yeah, this one is a very good picture. So you see there's a star, and you see how this star, because it has gravity, it warped the space around it.
Yeah.
So, if there is a small ball,
it'll gravitate towards it, right?
That's right. It curves, but it is actually traveling in a straight line around the curved path. Yeah. So if there is a mass, it distorts the space around it. So this is a two-dimensional sort of a effort to visualize the gravitational, the space being warped.
Yeah.
But obviously, this warping happens three-dimensionally, in all directions.
In all directions. Okay.
In all directions. Yeah. So why is the moon rotating around the Earth? There is no force that is attracting the moon. The moon is simply going around the circle around this curved path. And it is actually just traveling a straight line. That's a different interpretation from Newton's law.
Okay.
Laws interprets everything as force, and also particle physics also interprets everything as force.
Okay.
So that's why this is so difficult to reconcile. Quantum physics interprets everything in terms of force and particles and things like that, but gravity used to be thought as force, but now it's simply a geometry. Gravity is simply geometry.
What about the graviton?
So graviton is an attempt by particle physics to interpret gravity as force, but general relativity says gravity is not a force. It's geometry.
It's geometry. Okay, all right. Two conflicting ideas. Okay.
Two conflicting ideas. Yeah. So general relativity worked really well in its own context, in its own interpretation. It worked perfectly well. As you can see, light is bending. Why is light bending? Because the space-time is curved. Not because there is force.
Not because there is force, all right.
Yeah. So one of the effects of general relativity is light bends. So there's a star, actual position here, but curves like this. So from Earth's perspective, we follow the trajectory of this light.
Yeah.
Then we think that it's here, but rather it's actually here. Another one is a gravitational lensing. So there is there's like a very, very massive black hole here.
Yep.
And there's a huge Milky Way, a galaxy, which shouldn't be visible. But we see so light from here goes out in all directions, doesn't it? This
Yes.
way, that way, that way, and some of the light that goes out this way can curve around this massive object and arrive at us, detected. And if we simply follow the trajectory of this, we think that this object is somewhere there and there. So it's actually a circular thing. So you can see that this one appears. There's a massive object, so like a big star.
Yeah.
Or it could be a black hole, but in this case, I think it's a star. And there is a huge object behind this one.
Mm-hmm.
And it curves around this object, and it appears as if it's a circular disk.
Okay.
So that's one of the other effects of gravitational, the fact that, space is distorted. That fact causes the light to bend around it and still be able to be detected. That's called the gravitational lensing. So I can show you gravitational lensing. Have you watched the movie Interstellar?
No.
Pretty famous movie. Maybe you were a bit too young to understand when this movie was released, but it's definitely worth watching after the exam.
Okay. Mm-hmm.
And you will definitely, this is a gravitational lensing here. So there's a black hole here.
Okay.
And there's a massive galaxy behind it. And there are objects behind it. They bend around this. And
bend around this.
Yep. So you can still observe the galaxy behind it in a ring.
Okay.
Yeah. Have you heard about gravitational redshift?
No.
I don't think that's going to show up. What about the event horizon?
No, we haven't done that. No.
Okay. Chandraska radius?
No.
Never heard of that? Okay.
No.
All right. Let's have a look at your first outline. Shall we just try more special relativity questions now?
Actually, I have one Feynman diagram question I want to go through.
Okay.
It's the wait. How do I do this? Can I just send a photo through Facebook and then you can get it?
Yep.
All right. Just give me a second.
That's it.
It's sent.
Yep. Okay. So, what is this about?
It's a kaon going into a positive pion, and then negative pion. I want to know how you draw the Feynman diagram for that. It's kind of confusing, and I had to glue on interaction in the answer, so
right.
I didn't really understand it.
So it's a kaon And it's positive, is it?
Yeah.
It's a U and then S, is it?
Yeah, anti-strange, yep.
And then this is turning into pion.
Positive.
Positive.
Anti-down, yep.
Mm-hmm.
Both of them, two of them.
Two of them, okay?
Two of them, yep.
Pi plus and then U down this one.
And then pion, negative pion.
And then pi, okay. The negative pion, so it must be the opposite.
Yes.
I guess. So did you verify that this equation is possible?
Yes.
All right. So it is. There's a gluon involved, is it?
Yeah.
The U, and then S. This guy here turns into. So you need to draw a Feynman diagram for this one, do you?
Yeah.
Right. Okay. You look at the. Well, how is this one possible? Because there is no. The strangeness is not conserved. Charge is conserved, definitely. Charge is conserved because it's a plus, and plus 1 is equal to plus 1, and plus 1 and minus 1. The area number is 0 equals to 0 plus 0 plus 0.
Yep.
Lepton number is also 0 equals 0 plus 0 plus 0. But there is a strangeness.
Strange is not conserved.
Well, I think for strangeness for anti is positive 1. And for this, there's no strange here, right?
No, it's a 0. No.
So I don't think it's possible. Can I see the answer?
All right. I'll send you the answer right now. Here. You got it?
I think so. So look. It's an open up. Hold on.
It's not loading?
It's somehow it's not visible. Let me have a look at it with my phone. Okay. Let's have a look. So this is a kaon. So we'll just assume that this one is, so this is a particle, and this is an antiparticle.
Yeah.
And through this one stays the same, no interaction, stays as U. And this one interacts through a W plus, and then decays into two parts, which is the down, the anti-down, which is a pion. And it's really confusing. So the strange can turn into the W plus and the anti-U. And then this is a blue one. So it's definitely a much more advanced one. So to understand this, we need to know what kind of gluon can be emitted.
Okay, all right.
So it's a pretty complicated one, but I can teach you this if you want.
Yeah, this is just out of curiosity. Even though our teacher gave us this question, he said we won't be testing the test. I wanted to exactly know what does the gluon do in this situation. Well, I understand it's got something to do with strong forces. That's it. I wasn't able to find anything else about it.
Yeah. Let's have a look at color charge.
Color charge, okay.
Have you heard of this?
Yes, I have. Red, blue, green, right?
Yep. So color charge. It's really interesting. There's a red, green, blue, and then there's anti-blue,
Yeah, okay.
anti-green, anti-red.
Okay.
So the quark colors. So there are so gluons can carry one color and one anti-color.
Okay. All right.
So the quark anti-colors also combine to be colorless. All three colors combine to give colorless as well. So hadron, so this is a hadron. Hadron is something that's made up of three quarks, right?
Yes.
Before a color change. Now, have a look at this. This blue color emits a blue
Yeah.
and an anti-green. So think about this. From this blue, let's say blue color came out.
Yeah.
Then this will be colorless.
Yes.
But instead of that, it also emits a anti-green. Then it'll remain as green, true? Because think about this.
Okay.
If this one goes back in here, then this green
will turn back into blue.
And the anti-green will cancel out, and the blue will show blue, right?
Yeah.
So you can see that that turned into the green. This turned into green, and this will turn into blue.
Yes.
So that's what's going on. So you can see, like, many things can happen. You know, this can be up quark with green, up quark with red, and things like this. You know. That's quite important now. Let me have a look at this. What's the charge on strange?
Charge on the strange is -1 on 3.
So this one is a strange. So it's -1 on 3. So +1 on 3.
Anti-strange, anti-strange.
Anti-strange would have a charge of a +1 on 3.
1 on 3, yes, yes.
That's +1 on 3. This one has +2 on 3, right? So that's why it has +1. This one goes and then emits a
positive boson.
A positive W boson.
Yeah.
Then this will be charge of how much? This is up quark. Anti-up must have a charge of a -2 on 3, right?
-2 on 3, yes.
-2 on 3. For a question like this one, you really cannot predict something like this one. You have to learn this through experience. So I don't think something like this can be pulled out just by looking at the equation. The simple ones you can draw.
Simple ones we can.
Yeah, but for a complicated one like this, you have to learn them through looking at examples. Like this one here. So it's 1 on 3 turning into +1 and then -1 because if you combine them together.
Yeah.
Yeah. So this one is turning into this one here.
This one here. Okay.
That one there.
Yep.
And then this one here as well. And later that one as well. So that one, that one, that one, that one, that one, and that one as well. All of this. That makes sense, right? Because this one is U, and that's where you are here.
Yeah.
So strange is such a big, big particle. That's why.
That's why it's possible.
That's why it's possible to break it into all these smaller particles. Now, you have the W plus boson changed into this one here, spit it out the U.
Yeah.
U and the W plus. Now we need to look at this part here. Okay. W plus is also a pretty heavy molecule as well. Now let's see what happens when it spits out the anti-D. So anti-D, it's got a charge of 1 on 3.
Yeah.
So it's got a charge of 1 on 3. So this one should have a charge of 2 on 3. This intermediary here. But this splits into U. U has a charge of how much?
1 on 3.
2 on 3.
2 on 3, 2 on 3, yeah.
2 on 3.
2 on 3.
So this is pretty much the path of a U. So this here is path of a U.
U. Okay.
Yeah. But then from there comes out a gluon. So gluon contains a charge
Of 0, right?
of 0. That's right, of 0, charge of 0. But it's got color and an anti-color.
Okay.
Color and anti-color. So this splits into. So you just need to think that the W plus is splitting into this one here and this one here.
Okay.
And this is quite energetic. That's what from the U comes out this gluon. And there is really no way to predict this one. It's just an energetic one. So this one produces some gluon.
And then that produces charge.
And this is pretty much just a gluon, which is a boson.
Yeah.
And this one splits into 2, 1 quark and 1 anti-quark. And these 2, of course, they can annihilate, true? The anti-quark and
that's 0 charge. Okay.
That's got 0 charge.
The charge. Okay, that's
got 0 charge.
Okay, you're right.
So all of this is possible because this strange is such a massive. It's a very, very big guy. So have a look at that. That's 0.1, and look at these energies here. I mean the masses. 0.003, 0.006.
Okay.
Yeah, and W plus is also quite massive as well. So you can see that this one is just a U. Splits into W plus. And the W plus splits into U again. D anti-D.
Yep.
And this energetic U here, it's got a lot of energy in it. It just releases a gluon.
Is that the type of when? So what type of quarks actually release a gluon? So up quark releases a gluon. Is there any other type of quark that would release a gluon?
Yeah, all of them can release gluon.
All of them can release gluon. So up, down, strange.
Yeah, all of them can.
All of them can. Okay, all right. I see.
But there's really no way to predict this one because it's because anyone can do anything.
Anyone can do anything.
Yeah. So this, I would say, this is just a one. I think there's a few other ways. So, for example, you see how this W plus released a D anti-D here.
Yeah.
And then see this. So this anti-D could have gone to this one over here.
Okay.
See, and then this gluon could release another anti-D that could have gone over here.
Okay.
Yeah.
All right.
You have another difficult equation?
No, that's the only difficult equation he was able to give us.
Right.
I don't think he'll release any more, but yeah.
But did he say something like this could be in the exam?
Well, I don't really trust him. Well, I don't really trust him because this is Narbunda exams after all. But he said something like this probably won't end up in the exam. He said probably won't. I don't exactly trust him that he would not give a question like this.
So the W plus. So yeah, the reality is the W plus can just decay into some. So normally W plus just decays into D antiquark and then U quark without really necessarily producing a gluon like that.
It doesn't have to produce.
It doesn't have to. Doesn't have to.
Yeah. Okay.
But in this particular case, it does. And a gluon always comes from a quark, doesn't it?
Yes.
Yeah. So that's why this gluon is coming from this quark, and that's producing this D antiquark and D quark, which preserves the charge and everything. But something tells me this is wrong because this is a strange here. Then strangeness must be conserved. So if you look at the conservation of strangeness, says strangeness conservation requires a total strangeness of a reaction or decay is the same before and after interaction. Strangeness conservation is not absolute. It is conserved in strong interactions and electromagnetic interaction, but not in weak. Okay, but maybe that's the reason. There was a weak interaction here. Yeah. So the fact that the strangeness is not conserved sort of gives us a clue that there must be some weak interaction producing WZ boson.
Okay, right.
Yeah, it's not absolute. That was the reason. Okay, maybe a few relativity questions.
Yeah, so yeah, go ahead.
Okay. All right. There was open Gale-Force Relativity problem set 7. So this one is quite an interesting one. All right, so here's the problem.
Okay.
So I want you to try this. I think something like this could definitely be on the test. So the Earth and Sun are 8.3 light
minutes
apart. Ignore their relative motion for this problem.
Okay, so this
Earth is the Sun.
Yeah.
Event A and B occur at time equals 0 on Earth and 2 minutes on the Sun, respectively. So this is event A here.
Yep.
Happens over here, and the time is 0 for that. Event B occurs here at time equals to 2 on the Sun.
On the Sun.
Find the time difference between the events according to an observer moving at, so there's another guy moving at velocity equals to 0.8 c. That's right. Repeat if observer is moving in the opposite direction. So we need to use this equation. So we're looking for the time difference, right? Time difference. So delta t.
This is a Lorentz thing, right?
Yep, Lorentz transformation.
Okay.
Delta t. This is a t dash.
Yeah.
And this is delta t minus v delta x over. So this is nothing there. Over c squared.
Yeah.
So we are looking for the time difference according to the spaceship. So the gamma is 1 over. So that guy is how much is the 1? So there's 1 minus 0.8 squared, right?
Yeah.
What's the delta t, Navid?
Delta T. 2 minutes.
Yeah, 2 minutes.
2 minutes, yeah.
It's 2 minutes. Minus, what do we do this one? What's the delta
0.8.
So this will be
0.3 light minutes, yeah, okay.
0.8 C.
C.
That's a C square.
Right, yeah.
And then the delta X is how much?
8.3 light minutes.
8.3 light minute, right? So
Yes.
whenever there's a word light, you can actually use a C. So the C
Okay.
square
Cancels out. Ah.
That's how they go.
Okay.
So this is a 1 over root of 1 minus 0.64, and then 2 minus 0.8 times y, 8.3. That. So that's a 2 minus 0.8 times y, 8.3. And then, oh, it's negative. Divided by root of 1 minus 0.64.
Yep.
So this is a negative 7.7. What does the negative sign mean? So the time interval is negative 7.7, which means B happened first, and then 7 minutes later, this one happened.
Okay.
7.7, because it's negative here. Does it all make sense to you?
Yes. Okay.
That's possible because the spaceship is moving toward the sun.
Yes.
So the light from here could reach this guy first, and then
So then it will be that one. Yeah.
Yeah.
Okay. Okay. All right. Yeah. Good.
Yeah. Could this cause this one, or this cause this one?
Could this cause this one? Don't we have to check the velocity of light? Don't we have to check the velocity to see if it's above C or not?
Yeah, that's right.
If it's above Z, then it's not possible. If it's under C, then it's possible if one event causes the other.
Yeah. So in either frame, let's think about this.
Yeah.
So the distance between these two is
8.3 light years.
So let's talk about the Earth's perspective. You shouldn't be calculating the causality from this guy's perspective.
Okay.
Yeah. That's what we learned for last time. So this one is the 8.3 light minutes, but it was taking 2 minutes, right?
Yeah.
2 minutes. So it means it's faster than the speed of light, isn't it?
So that means A can't cause B.
That's right. How can, because it's 8.3 light minutes away, if this happened first and that caused this one, then that should happen at least 8.3
minutes later.
So this cannot, this violate the causality, right?
Causality, yes.
I mean, doesn't violate causality. So this cannot, if this is caused by this one,
yeah,
that violates the speed of light.
Yes.
So therefore, this cannot be caused by A. Yeah. So that's what we can write. So A cannot cause B, or B cause A. Okay, because they are separated by 8.3 minutes. And B happened 2 minutes after A. So this violates the speed of light. Okay. If the spaceship is moving toward the Earth, then what you need to do is change the sign of this to positive.
Plus.
Then what you're going to get for the delta T for the observer is going to be 2 plus, so that's going to be 2.
Yep.
Plus, 2 plus
0.8 times 8.3, right?
0.3 times 8.3, that's right. Divided by a square root of 1 minus 0.64. And it's going to be 14 minutes, which means that one happens first.
Yeah.
14 minutes later, this happens. So this will have to catch up the spaceship, right?
Yeah.
And you are traveling toward this signal here, so that's 14 minutes later. So something like this will, I think, definitely be there.
Definitely be there. Okay.
Have you also done something called a space-time interval, S?
No, I
Always
have
constant.
not. I have not heard of that. No.
Never heard of this?
No.
Okay. But this is quite useful stuff. There are many, many interesting questions, but definitely don't have time to go through all of them. Okay, any question from the worksheets that you have tried?
Oh, the worksheets, no questions from there. They didn't give any good hard questions from there.
Okay.
There was no good hard questions. Not from our worksheets, no.
Okay. But have you gone through all of them?
Yes, I went through all of them. Yeah. School worksheets and everything.
School worksheets. So even the relativistic kinematics?
Yeah.
Pretty good. Yeah, I couldn't find any really hard question either from your school worksheets. But that's usually the case, you know. Narabanda is just there.
Yeah, they don't give anything hard
for
beforehand.
Radford and Girls Grammar, they pretty much stick to their worksheets, you know, when they give out questions on the exam.
Yeah. But Narabanda courses don't do that, no. Not at all.
So I'll send this one to you. There are some, I think, interesting questions here. So definitely this is worth a try. You can study this one tonight and let me know if you have any trouble.
Sure. Can you also send me a recording of the previous lesson and this lesson so I can catch up on Lauren's diagrams again?
Yep.
Thank you.
No problem. So you can see that this question, this worksheet also goes through some momentum, relativistic kinematics.
Okay.
Very quite hard questions as well. And also this one is a very useful formula, which is this one here. So this one sometimes can be used because it doesn't matter what frame you're talking about. In every frame, c delta t squared minus delta x squared. So these values can be calculated from the Lorentz transformation, right?
Okay.
They will always be the same. So this one squared minus this one squared.
Okay.
So it's an interesting property. So for the Earth case, we can see that c times by time, this was 2 minutes, right?
Yeah.
So this is a 2 squared. Let's have a look. So this is in Earth's frame, 2 squared. The events were 2 minutes apart.
Yeah.
And one of them happened on Earth, one of them happened on the Sun, right?
Yep.
So this was 8.3 squared, isn't it?
Squared, yeah.
Yeah. Hold on. That cannot be negative. Why is it negative? Delta x. That's 8.3 c delta t. So it'll give you negative, right? Time was because that's square, should be negative.
Yeah. It can't be negative, no.
So this is another question showing us that in 2 different frames, yeah, they agree, 25.
25.
Yeah, this is another type of question, but this one here. Yeah, why is this giving us negative? All right, let's assume that it's negative, but then if you look at the another perspective, you can see that the time is 7.7. So that'll be the 7.7 here squared. 7.7 squared minus. Oh, we didn't figure out the length. That should be. Let's not worry about this one here.
Okay.
But you can go through this worksheet. It's definitely a harder level than your Narabanda one.
Yeah.
What time is your exam tomorrow?
12 o'clock.
12 o'clock. Okay. So go through this one also tomorrow, tonight and tomorrow morning. Let me know if you have any problem. Okay. I'm happy to give you some explanation.
Sure. That's good. Thank you.
Okay. Yeah. Well, good luck tomorrow.
Thank you.
I'm quite free tomorrow as well, so just let me know if you have any questions. Happy to answer.
Thank you.
Okay.
See you.
Bye.
Bye.